What if time isn't fundamental? What if it's not a dimension we travel along, but something that actually emerges from the fabric of the vacuum itself? Well, today we're diving into a pretty mind-bending framework called dynamic vacuum field theory, or DVFT. It suggests a wild new origin for time, quantum mechanics, and even the arrow of time. And believe it or not, it's all tied together by the geometry of pi. So, let's start with the big question. Is time even real? I mean, physics has a bunch of different definitions for it, but no single unified picture. This new theory, DVFT, it just cuts right through all that and says something completely different. It says time isn't a thing that exists on its own. Instead, time is what a dynamic vacuum does. It's a process. All right, section 1, a new theory of time. We're going to move beyond this old idea of time as some kind of dimension or cosmic container and start thinking about it as a real physical process. Now, to build up this new idea, you first have to tear down the old one. So DVFT starts by rejecting some of our most basic assumptions. It says, look, time is not a fundamental dimension like space. It's not some kind of cosmic river that flows all on its own. And this is a big one. If everything in the universe just stopped, completely froze, DVFT says time itself would cease to exist. So if time isn't fundamental, what is? Well, that brings us to the absolute heart of the theory, the vacuum's phase clock. The idea here is that the answer lies buried in the properties of the vacuum field itself. Okay, don't let the equations scare you. This is how the theory models the vacuum, as a complex field. For all the physicists watching, this phi here is the fundamental degree of freedom. But for everyone else, just focus on the two parts. You've got rho, the amplitude. Think of that as the inertia or the substance of the vacuum. And then you have theta, the phase. This is the game changer. In DVFT, theta is the clock. And here it is, the core definition. This basically says that the passage of time, dt, is just a count of the change in that vacuum phase, d theta. It's a direct one-to-one relationship. When the phase changes, time passes. If the phase progression stops, time stops. Simple as that. The speed of that change is just set by this local rate, omega. And this is where it gets really powerful. This one simple definition has these huge, immediate consequences. So what is a clock? It's just anything whose behavior is tied to the vacuum's phase changing. What's time dilation in general relativity? Oh, that's just the local vacuum phase slowing down near a massive object. And an event horizon around a black hole? That's just a place where the phase progression grinds to a complete halt. It's incredible how it all just clicks. All right, let's move on, because this builds to something even deeper. The theory actually connects this idea of a phase clock to the very origin of quantum mechanics itself. And it all has to do with the simple geometry of a circle and the number pi. You see, here's the key. The phase, theta, it's not a number line that goes on forever. It's an angle on a circle. It goes around and comes back to where it started. And a full circle, as we all know, is 2 pi radians. This one simple fact that phase is cyclical is what gives rise to all of quantum mechanics. And this slide just walks us through the logic. It's beautiful. First, for any stable process, like an electron in an orbit, it has to complete a full cycle, so its total phase change has to be a whole number of 2 pi turns. Makes sense? Second, we can define a quantity called action for one of these cycles. Third, we just have to propose that this action comes in little packets, it's quantized, and what's the result? Boom, Planck's constant, h, isn't some magic number pulled out of a hat. It's simply the amount of action in one 2 pi turn of the vacuum's phase. This quote just says it perfectly. Planck's constant is the quantum of action, but it's normalized by 2 pi. That division by 2 pi isn't just a mathematical trick. It's there because phase is an angle. It's geometry. This directly connects the shape of a circle to the granular, quantized nature of our universe. It's profound. Okay, so this theory gives us a definition for time and a reason for quantum mechanics. But what about one of the biggest mysteries of all, the arrow of time? Why can't we remember the past but not the future? DVFT actually proposes a physical mechanism for this, not just a statistical argument. To get there, we have to rethink entropy. We're all taught that entropy is disorder, right? But that's kind of vague. DVFT is way more specific. It says entropy is a measure of phase decoherence. Think of it as the scrambling and irreversible loss of information about how the vacuum's phase is organized. And once you have that new definition of entropy, the arrow of time becomes stunningly simple. The forward direction of time, it's just the direction in which phase information becomes more and more scrambled. Time doesn't flow forward. The vacuum's phase simply evolves toward a more decoherent state. This table really drives the point home. Look at our other big theories. Classical mechanics, general relativity, they have nothing to say about why time moves forward. Statistical mechanics gives us entropy, but it kind of has to assume the arrow of time to begin with. DVFT is claiming to be the first theory where both entropy and its constant increase pop out naturally from the underlying dynamics of the vacuum. So why does this scrambling always increase? Well, the idea is simple. Just like a drop of food coloring in a glass of water, any concentrated phase information just naturally wants to spread out. Every time particles interact, every time light is emitted, little bits of that phase correlation are carried away and scattered into the vastness of the vacuum. And trying to gather all of that back up again, it's basically impossible. So let's bring it all home. We've seen how DVFT builds a definition for time, explains quantum mechanics, and even tackles the arrow of time. Now, let's look at how all these pieces fit together into a single, elegant picture. This is really the money shot. This is the grand thesis. Time, entropy, the arrow of time, they aren't separate problems to be solved. They're all just different symptoms of a single underlying cause, the natural evolution and relaxation of this vacuum phase field. So let's just recap the whole thing. Time? It's just the story of the vacuum's phase unfolding. Quantum mechanics, with its constant h, that's a direct consequence of phase being circular, a 2π geometry. The arrow of time? That's just the inevitable spreading of phase information. And the hero holding it all together is pi. It's not just some number, it's the constant that makes the whole system work, making time stable, cyclical, and ultimately quantum. Now, whether this theory turns out to be right or wrong, it forces you to think. It makes you question everything you thought was fundamental about the universe. And it leaves us with this one final, massive question. If time itself is just a trick of the vacuum, what else might be hiding in the properties of empty space?